Let me describe methods of computing S. One is this just described matchup argument. So you have to find out that, so you separate the diagram into vertices and the links, I mean the propagators. So I'm considering this diagram. So first you break it up into the two vertices and the three propagators. Okay, this is the calculation. If you remember earlier, I was describing it in this way. Then you ask the question, so each one of them, as I just discussed, that each one of them will come with certain factors in the denominator. For example, this vertex has a factorial 1/3 in the denominator, with factorial 3 in the denominator for interchanging of the three derivatives. Similarly, this one, and each one of these links, each one of these propagators has a factor of 2 downstairs, corresponding to interchange of these dots within itself. And then finally 1/factorial 3 outside of this disconnected piece. This is a disconnected piece from the point of view of the free theory, right? So that has a 1/factorial 3 because the interchange of the propagators. Okay, so let us see if there are matchups. You see, when you connect this, and this, then interchanging these derivatives among themselves and interchanging these three propagators have the same effect. If you interchange among themselves, that also automatically interchanges among these propagators. So that's a matchup, and that matchup actually that costs factorial 3, and the corresponding to that matchup, you would get a factor of factorial 3. So this interchange of derivatives and interchange of propagators are matched up. Here and here, interchange of derivatives and interchange of propagators are matched up, and that contributes a factorial 3 in S. Once that is done, once you have fixed that, connected this, then interchange of these derivatives are not matched up, because you can make genuine changes. Those changes are there. So this interchange among these, it's only one of them is matched up with the interchange of the propagators. So that's why this is not matched up. This is matched up according to your, depending on which way you view it. So that gives a factor of factorial 3. The other one is the interchange of the two vertices, right? The prefactor of 2, the interchange of the two vertices will have a factor of 2 downstairs, and each one will have a factor of 2 downstairs because of the interchange of the two dots within itself, right? So the matchup here is the interchange of the two vertices and interchange of flipping the propagator for all the propagators, or interchange of ends of all the propagators together, then only it matches. So of course, interchange of the two ends of a propagator, each one has a factor of 2 downstairs. But if you interchange the two dots of all the propagators together, that will also cost only 2, right? So factor of 2. So that is another factor. So this is interchange of vertices and interchange of ends of all propagators. Are matched up. And that gives a factor of 2. And therefore, the result for S is factorial 3 times 2. You can use the same method for getting the result is equal to 2 for the first diagram that we evaluated, which is this one. Again, the method says that you separate out the vertices and the propagators. And of course, here only one vertex. So you have interchange of 3 vertices. That has 1 over factorial 3 factor here. But here the matchup is interchange between two derivatives of the vertex, and interchange between the 2 points, 2 endpoints of the propagator. That is matched up. So you are connecting like this. So these 2 is a matchup. So interchange between 2 derivatives and interchange between 2 endpoints of the propagator are matched up, and that gives you is equal to 2. You can use the symmetry argument. Let's look at the symmetry argument, because we said that for each matchup is related to a symmetry of the diagram. So let us look at this diagram. Then of course, there are 2 symmetries. One is the interchange interchange among these lines. These are the 3 lines. This line, and this line. You can interchange among themselves. And of course, if you do, then the diagram does not change. And of course, if you interchange the 2 vertices, then also the diagram doesn't change. So the symmetry is interchange among lines that gives factorial 3, and it interchange between vertices that gives you 2. That's total symmetry factor, factorial 3 times 2. And similarly, this diagram, if you look at that, there is also a symmetry. That symmetry is not I mean, you cannot see it as interchange of 2 lines or vertices, but you see there is an orientation change. If you look at this diagram with an orientation, then of course there is a transformation which goes from here to here, where the orientation changes. This is a twofold twisting the loop. So this is twisting the loop, and there are two. This is a twofold transformation, and this gives S equal to 2. You could use the same symmetry argument for this diagram. Right? So in this diagram, the symmetry argument is that there are two loops. The two individual loops can be twisted. You can twist this loop and this loop, and then interchange this, interchange the two vertices. So this will be independent twists of two loops and interchange of vertices. Two vertices. This is a symmetry, and that gives you S to be equal to. Each one is twofold. The twist is twofold. There are two twists, each contributing a factor of 2, and the interchange of two vertices is a factor of 2, so 2 cubed. So that is the symmetry factor. Next, what we need to do is to look at this disconnected diagrams. Just like in the free theory, in identical component of a disconnected diagram will have a symmetry factor 1 over factorial n. In the interacting theory also, that same thing should happen. Then only our analysis that takes us from that enables us to write Wj as exponential of Zj, Zj being the set of connected diagrams. That argument goes through. So that is what we want to look up in the how that argument goes through in a specific case, which is, we have looked at the vacuum diagram here with 2 vertices. If we look at the vacuum diagrams with 4 vertices, if we look at the term vacuum diagram corresponding to vacuum diagram with 4 vertices, then hidden in that term there will be some disconnected pieces. Though there will be connected pieces, there will be also some disconnected pieces, which has to be exactly square of the vacuum diagram with 2 vertices, and that must have a 1 over 2 as a symmetry factor, because it's a square. Okay, that's what we are going to verify in the next part. Yeah, so calculation of this symmetry factors and phi cube perturbation theory has been extensively discussed in a QFT lecture note by Mark Srednicki, which is available online. So QFT lecture by So much of my discussion is followed from there in the last few lectures, that last couple of lectures where I'm discussing phi cube theory. So this is a reference.